Now we are going to meticulously set up the precise dose curve for the 45-degree test. First, you will receive a specific file that you absolutely need to carefully copy onto the designated memory stick. Please save it securely here. Then you will insert it into the appropriate slot. After that, you will open it. Next, we will then call it up on the system. We will press this particular button. By holding it down firmly, we will carefully select the desired option. This is precisely the test we absolutely need. With this particular file, it will undoubtedly be much easier to properly set up everything. We simply press the button and the file immediately appears on the screen. It clearly indicates free, and we can then effortlessly unlock it with any available button. Next, if this specific button doesn't seem to work as expected, we will then need to carefully navigate to the main menu and proceed to go to. We need to carefully set the operational settings so that at the very bottom, specifically under function 2, we can precisely go in and set it using the lower control buttons. We will effectively control the entire lower line with these dedicated lower buttons and the upper line with these corresponding buttons. At the very bottom, it should clearly display recall data. Then we will press the OK button, and in this particular instance, we will proceed to press it. And we call up the probe that we need. It may already be calibrated, so we can easily find it here. Usually, it is recorded by serial number and by angle. We select 45 degrees. What do? The first thing we check is to make sure it is set to 2 MHz. This probe uses 2 MHz for thick metals. For large thicknesses, that is to say, when dealing with a significantly large probe, we utilize specific settings. Conversely, for small thicknesses, we consistently employ a 4 MHz frequency. Subsequently, it is crucial that we meticulously check to ensure the angle of the probe is precisely set to 45 degrees. To accomplish this, we carefully press the joystick within the menu interface, navigate to the appropriate section here, and then verify that the probe's orientation is indeed accurately positioned at 45 degrees. We set it to 45 degrees, press again, 45, OK, confirm. The thickness should be set. The calibration block in our case is 85. It could be 40. The standard is 40, but there could be other values. We are not setting X-wall for now. We are setting it so that reading 1, 2, 3, 4, 5, and so on are configured as shown here. Next, for the moment, we won't be touching the DAC. We will carefully set this particular configuration. This is configuration number 2. In this specific case, I'll make a slight change so that there's a clear arrow visible here. We are currently setting up the joystick, and we are meticulously configuring all the functions so that they operate correctly. This includes a long press, followed by a short press, then another long press, and finally another short press. For the first function, we go into the first function and set the envelope as it's convenient using the joystick. You'll see later. For the second function, we set up freeze, but not with the joystick, with these buttons instead. Then we confirm. We confirm this initial step, then seamlessly move on to the second crucial focus area and also enter this new section with a simple single button press. Here, within these detailed settings, we meticulously set 80% of the screen for optimal viewing and data recall, which allows us to efficiently call up and access our previously saved file. After ensuring everything is correctly configured, we confirm these settings. Moving forward to the next series of important adjustments, we proceed to turn on the envelope function, which is essential for further processing and analysis. We check the next settings, everything is done, we exit with a long press. Now what do we need to do? Erase the DACs. Again, we go into the menu, go to the DAC function, scroll up and down to delete curve, press it once, and within 5 seconds, we need to press it twice. Please press this specific button. If you don't manage to make it in time, you should then go back in here and press it twice, and that is precisely how you effectively erase the DAC. After that, you can exit from this location and the DAC will be completely set. Next, it is important to carefully check that the speed in velocity is approximately 3250 and the probe delay is around 8 and on. We meticulously adjust the beam on the B2 block so that it precisely corresponds to an exact 25 millimeters, and consequently, the very same signal will be accurately reflected and ultimately result in a full 100. Then we carefully take block 2 and diligently find the maximum amplitude. In this particular case, we judiciously reduce the range as it is currently far too large. So just once and with great care, we press here, select envelope, then reduce the range so we can see two signals, lower the decibels a bit. Next, we need to move the gate closer. How do we do that? We find the gate. First, carefully move it toward the signal, ensuring precise alignment with the visual indicator. Then, with deliberate control, slightly decrease the width in this specific area, making sure to set it precisely to 40 units. Now, we meticulously proceed to look for the maximum amplitude, executing this step exactly like this. Carefully place the measurement tool directly onto the designated block and initiate a thorough search, diligently making sure to capture and identify the absolute highest values available within the specified range. And then the amplitude function meticulously triggers at precisely 80 degrees. Once again, we carefully remove this particular envelope, and now the signal, indeed the precise envelope, clearly shows us the exact and highest peak. Now we deliberately move back and forth and gently tweak it a little bit left and right, diligently trying to find the absolute maximum signal possible. Again, 80% amplitude, we try to find the maximum. We look for it very carefully. Next, we go back to AutoCal. Let's proceed. We proceed to press the designated record button, initiating the recording process, much like this demonstration. We activate the record function. Subsequently, everything functioned perfectly and without any issues, confirming the successful activation as we press it, ensuring the capture of the desired content. We press the record button once, like this record. Everything worked fine this time. We press it again, a second time, and the button is recorded. Next, we move the gate to the second signal without moving the probe, just move the gate. We adjust the signal to 80% of the screen, just like that. We set it and then press this button once so it works. To do that, we need to exit to the main menu. We press it. There, it worked. Then we go in and record the signal using this exact button. It's recorded. Here the speed is 3254. We check it, exit from here, and the speed is 3254. And the probe delay was meticulously set automatically, ensuring optimal timing for our measurements. After we have carefully and precisely set up the beam, aligning all necessary components, we can then double-check its configuration and performance on the large K1 block, which serves as a crucial diagnostic and verification tool. Let's proceed to accurately measure the beam's intensity and characteristics. It should ideally equal exactly 100 units for our experimental parameters. Following this critical verification, we then carefully and strategically place the probe into its designated position, preparing for the next phase of data acquisition. Again, we carefully press the lower button, which then precisely sets the display to 80% of the monitor's full capacity. Following this, our objective is to meticulously find the absolute peak maximum signal. To achieve this optimal signal strength, we must deliberately move the sensor or device forward and then back, and also gently maneuver it a little to the left and then to the right, ensuring we thoroughly explore the area to pinpoint the strongest possible signal detection. And we meticulously look at the SA value. SA here profoundly shows us the decibels precisely indicating the overall strength, the significant strength of the defect amplitude. So the lower the amplitude, the smaller the signal, the smaller the defect. The closer the amplitude is to 1 to 0, the better the condition of the material. This is a crucial aspect for accurate assessment. A higher numerical value means it is indeed stronger, so the measured depth is 70, and the radius, then this particular measurement represents the depth, and r will be the precise distance from the very start of the probe to the detected defect, and the exact site is thereby obtained. Good, moving on to the next step. What exactly do we do next? We need to find the X-wall in the calibration process. In this specific case, here is the X-wall. How precisely do we find this X-wall? I will show you now. We take a ruler. In this case, there's a notch here, so we measure with the ruler. From this cut to the start, to the beginning of the probe, we need to measure with the ruler, and we need to turn on the flashlight. Where do we put the camera? We don't put it down. When you provide your invaluable assistance to me, I meticulously keep holding it firmly and steadily in place. We can clearly observe and confirm that from the precise commencement of the initial cut, all the way through to the careful and deliberate beginning of the probe's insertion, we consistently achieve a measurement of exactly 12 millimeters. Once this crucial measurement is accurately established and confirmed, we then proceed to carefully and precisely set it into its designated position, and subsequently we gently and smoothly go in with the instrument, ensuring every step is executed with utmost precision and control. What exactly is the x-axis offset? It's the precise distance from where the probe beam initially fires to the very start. We carefully take that into account. Here it is, clearly displayed, so that the machine, the device itself, accurately calculates from the defect's true start to the defect itself, not from the center, but exactly from its beginning. So we've set it to 12, and with that completed, we exit. Now, we can carefully check the precise angle to accurately determine if we truly have the exact 45 degrees that we are looking for. On the specialized calibration block, we will diligently find the clearly marked 45-degree indicator. We then meticulously examine the specific blocks. Here, we can clearly see the 40-degree mark, and the 45-degree mark will naturally be positioned right in the middle. Again, we will carefully locate the maximum signal, which represents the peak amplitude. So we will precisely adjust it in this particular direction to achieve the desired outcome. So now let's take a careful look. Let's precisely check the angle. The sample itself might not be exactly 45 degrees. If it was worn down unevenly, for instance, it could potentially be 46 or 47 or 43 or 43 and a half, and so on. Our x-axis measurement was 12 millimeters, so we will measure 12 millimeters from the designated start point, and then we will carefully check. So we get 12 millimeters. We go to this value. This value will be here, 45 here, and here we get 40, 43, 43. About 43.5 degrees approximately, or more precisely. So we need to set it to 43.5 degrees to be exact. It's best to meticulously sand it down with fine grit sandpaper so that it clearly shows a perfect 45 degrees. 43.5 is definitively confirmed and established. Next, we can already confidently start the precise calibration process up to the free one, which explicitly means that the initial first and subsequent second blocks are absolutely no longer required or needed. We carefully take the primary main calibrator and the essential shim block. The precisely drilled hole here will be exactly 3 full millimeters deep. We've meticulously set it to precisely 85 millimeters. We then proceed to start with the very first signal, which we absolutely do not. We do it like this. We remove it, set the range lower, move the view, and find the first signal. Here it is, the first signal. We listen to it carefully. We bring the gate up and perform a thorough check. Our objective is to find the maximum signal, which means identifying the point of the highest possible amplitude. The visual representation provided by the envelope will be an invaluable tool, significantly assisting us in accurately determining this peak value. Now, to provide a clearer and more unobstructed view for better observation and analysis, I will proceed to carefully move the block into a more advantageous position, ensuring that all relevant details are easily discernible. You can see it, right? Here it is, the signal maximum. We need to see where the probe is pointing. It's pointing almost from the center at a 45-degree angle. That's exactly what we set up for the first one. Now we'll double check if we found the defect correctly. Always look for the signal maximum. Let's connect left and right. Here we found it. Let's look at the monitor. It shows a DA depth of 4.5, depth 4.5. The distance to the defect RA is minus 8 millimeters. So we measure 8 millimeters from the start, and we can see that the probe is pointing exactly right here, right at this spot. O'clock, and the precise depth is 2 o'clock in the afternoon, and your measured depth is exactly 4 millimeters. We carefully check here, 4 millimeters, it's almost exactly at 3:30, precisely at this specific spot. Next, we meticulously calibrate the DAC. We then proceed to go into the DAC. We have successfully entered the DAC. And we carefully set the first crucial point. Then we press the record button. We proceed to the record function. And then we press the top button. This action effectively locks in the first primary point. We have successfully fixed it. Next, we meticulously move to the second designated hole. We must diligently find the maximum reading. Okay, now, let's carefully make the gate wider. Let's carefully set it to 80% of the monitor's display area. Then we find the absolute maximum value. We will then turn it gently left and right. Again, we find the maximum. Next, we check what specific kind of signal this is. The prominent green marker indicated by the arrow clearly shows that it's accurately catching this exact signal, not some other one. And it precisely shows a depth of 14.5 millimeters. And it's almost 2 millimeters to the object, that is from the start of the sample. Yes, it's really about 2 millimeters. And we check the depth, 14.51, and here we have it. Yes, about 14.51. So we found it correctly. We proceed. Go back to the DAC and record the second point. To record it, press Here, now we have the first DAC line appearing. Next, we take the third point, meaning they will go one after another in order. If we have a short calibration block and a reference block, then we will already be looking at the reflection if we don't have enough, or we flip the calibration block and then shoot from the other side, increasing the values so that our points are in ascending order, starting with the smallest, then larger. So, if in this case we take such a calibration block, we get a point in the center, we shoot, and the first signal will go straight. The second signal in this particular scenario will be completely reflected. That is to say, it will travel. If the very first signal we meticulously shoot directly at a precise 45-degree angle, then the subsequent second signal will undoubtedly go from this specific point here and then proceed downwards. And the third signal, following its own distinct path, will go from this initial position here to this next point and then ultimately return. So it will be thoroughly reflected by the presence of the hole, creating a distinct and observable pattern. And so on. That is, calibrating with just one hole is very difficult. The standard is usually 40 millimeters, and they send two holes, one a bit closer, the other a bit farther, one in the center, the other a bit closer. That way it's convenient. We can calibrate closer to the point. If the hole is on top, then you flip it over and shoot from the mirrored side. It's much more convenient this way. I have nothing against it. We set it aside. Next, we need to find the third point. Now we're looking for the third point. So we start the signal. Here's the signal. Let's check what this signal is. Set the monitor to 80%, maximum. Be sure to find the maximum. Because if we don't find the maximum, we'll get completely different readings for the maximum amplitude. And we see that the distance to the object is 11 millimeters and the depth is 24.5 centimeters. Let's check. 24.5 centimeters is exactly at the third hole, and the distance is 11.30 millimeters. That is 11 millimeters. So we mark off 11 millimeters. Yes, that's correct. We hit this point, so let's check the amplitude maximum once again. Our little angel helps us with this. Then again, we move upward and record by pressing the button. We've recorded it. And so on. We do this for all these points. We hit this point. So once again, we check the amplitude maximum. The envelope helps us with this. Next, we go up again and record. With a press, we record it, and so on. We check all these points, and at the last point, we then proceed. If the distance is sufficient for us, then we finish and it's recorded. If this depth is not enough for us, then we look at the reflected signals. We can flip the calibration block to the other side and try to hit the points there. When we're done, we press finish and we get a result. We look at how it appears. Here it is. In this way, next, we will proceed to delve into the actual DAC curve. We carefully enter it using the precise joystick control. That is to say, we have successfully entered and accessed the DAC curve, ready for further interaction and analysis. In this way, next we go into the actual DAC curve. We enter it using the joystick, that is, we've entered it, and with the joystick we can adjust additional functions. We go in and once again go up. So, as for transfer correction, for now we are not doing it. There is a second video where transfer correction is shown, how it is done and what it is needed for. Here, we need to set it up. By default, clutch is set so that we have additional lines making it more convenient to work, but simply this particular function absolutely needs to be properly enabled. Now let's carefully observe exactly where it is currently enabled within the system. it was recorded automatically. You simply needed to press the record button and it would turn on instantly here. Here, we can meticulously set up the precise acceptance and delivery criteria, whatever specific parameters we truly need for a thorough evaluation and final acceptance. In this particular case, it's currently set to a robust plus 12 decibels, then plus 6, and finally minus 6. And here they are, clearly visible between us. If we are meticulously inspecting an object and subsequently find some discernible defects, if we carefully approach a particular defect at precisely 0 decibels, it inherently means that according to the established calibration block, we've precisely set it so that this specific hole is approximately 3.3 millimeters in diameter. The closer we get to the object, the more detailed our inspection becomes. None to the nature of the imperfection or flaw, and the closer the defect is positioned to the outermost layer or boundary of the material, specifically referring to the prepared and inspected surface of our material, the more elevated and pronounced indication or measurement will invariably be. We can also make precise modifications or fine-tune the settings, which I will personally demonstrate for your understanding, ensuring it does not come into contact with or extend to the wedge component. TCG. So this will be a simple, perfectly straight line. This is a straightened DAC display. Some operators find it much more convenient to work in this particular way. It means the signal is always displayed at roughly the same consistent height. With a traditional DAC, the signal typically decreases, but here the defect will always appear at about the same consistent level. With an unaltered, perfectly straight and consistent amplitude. Personally, I find it considerably more convenient and efficient to approach my work in this particular manner, as it truly streamlines the entire process. Now let's thoroughly examine and explore what other valuable and diverse functions are thoughtfully incorporated and available here within this system. As for the crucial aspect of transfer correction, I previously mentioned and emphasized that it absolutely needs to be precisely and carefully specified, ensuring optimal performance and accuracy. This is essential because our calibration block differs from the actual material, and we need to determine this on site and enter it as a correction, and that's it.